Okay, class, we're looking, let's just kind of interface here, at the discussion of blood oxygen transport. What we had previously said is that oxygen is carried in the blood in two ways, on hemoglobin and dissolved. The lion's share on hemoglobin. The amount on hemoglobin is based on the status of the oxygen dissociation curve, and the iron is in the +2 state. What we want to talk about now is the oxygen dissociation curve. So that's what this particular video is going to concentrate on. We're saying that oxygen carried in the blood in two ways. Okay, oxygen here is carried on the iron as long as the iron is in the +2 oxidation state. If it's in the +3, which could be oxidized like with a free radical, it won't carry. In all of us, some of our iron is in the +2. Thank goodness most of it is, and some is in the +3. Now, remember when we talked about anemia and I talked about red blood cell counts, we said we had three things to look at the red blood cell count. The hematocrit, the hemoglobin, right? And the red blood cell count. I said of all three, the main one is hemoglobin. That's the one we use to transfuse and everything, because that's really what red blood cells are about. The amount of oxygen, and we said that about 12 to 16 grams per deciliter. I set it at 12 to 16 grams per deciliter of blood, 1/10 of a liter, was kind of the normal hemoglobin. Okay, so how does that equate to respiratory? The amount of oxygen carried on a gram of hemoglobin is between 1.32 and 1.39 mil. Now, generally, most will say, so an average, let me come over here, an average value, let's do that, an average would be 1.34. Now, why the disparity? Okay, idealistically 1.39. If all of the hemoglobin was in the +2 state, listen to me, if all of the hemoglobin was in the +2 state, that would be perfection, 1.39. But considering all hemoglobin is not, we got free radicals and everything running around. So therefore, the low side is generally 1.32, generally in normal range, unless you have a disease, a sickle cell or something. So we take a median value of 1.34. That's kind of the median value many will take to take a conservative approach. A conservative approach. Okay, let's go further now. So we want to talk about this, but for some of you, I need to kind of increase your knowledge a little bit before we get to that. So what I want to talk about now to explain that is graphing, because we use that a lot in science. Okay, so we're applying graphs to science graphs. Applying graphs. Now, you learned this in mathematics. Let's apply this to science. So let's kind of refresh our memory. For some, you'll be right on target and don't need this. Okay, y equals mx plus b is an equation of a straight line. M is the slope and b is the y-intercept. M is the slope, b is the y-intercept. Okay, in this equation, which you've learned before in a math course. All right, so I now have shown a x and y axis, and I've shown some straight lines, and I've shown some slopes. If you have a slope going straight up this way, that's what we call an undefined slope, or some will call it infinity. Because in math, it's the rise over the run. The rise over the run is how you come up with the slope. Rise over run. Rise over run. This is a positive slope. So any slope above this 0 are positive slopes. This here is a 0 slope. This is undefined. And any slope down this way would be a negative slope. Okay, that's refreshing your memory from what I know you did in high school and a math course in college. All right, so now we come with this. Now I'm going to apply it to a science graph. When we plot something with a changeable parameter on the x-axis, like say time, and I put this here because this is where this is, but let's say time, or tissue PO2, which is when we apply it here. and another one over here on the y-axis, some changeable parameter. It could be anything, gross national product for that matter, if you wanted to apply it to business graphs. In this case, percent saturation of hemoglobin. Then when a changeable parameter is plotted on the y to another one on the x, the slope of the line represents the rate of change. So if the slope goes straight up this way, it's an instantaneous rate of change, because if this was time, it's happening at the same point in time. Okay? A slope this way means some positive rate of change. A slope this way means some negative rate of change. And a slope this way means no change. If time was here, then that would say that no matter the time, nothing is changing. Nothing is changing. Okay? So this is involving the straight line graphs. Right? Now that's not completely straight line. So I go to this next one, and we're looking at a curved line, like a parabola in math. In order to get a curvilinear line, you take x to a power greater than 1. X to a power greater than 1. Okay? So y equals mx to a power plus b. That gives a curvilinear line. Now what does that say in science? Since the slope changes in the curved line, see the slope is changing, the rate of change itself is changing. See, with the straight line, it was a uniform change because you had the same slope all the way. But in a curvilinear line like this here, the rate of change itself is changing as you go along the x-axis. So I want to bring that up. All right? So now with that in your mind, now we can go and look at this curve here. This is called the oxygen association dissociation curve. Now, if we take it up this way, that's association. That means that oxygen is loading on the hemoglobin. Check this out. Oxygen is what? Loading on the hemoglobin. Okay? Loading on the hemoglobin. Now, where would that occur, ladies and gentlemen? That would occur up here because it's in the alveoli that oxygen is loading. So going up this way would be oxygen loading. Okay? Going down this way would be it unloading in the tissue cells. So loading and then unloading. Okay? Now remember, we're looking at both. So we're going to start first, let's say, with the loading aspect. Okay, the loading aspect. Now, what did we say the partial pressure of oxygen would be coming into the lung? We said it would be about a 40. So therefore, right here would be a 40 right there. That's a 40. That's in the tissues. Because see, down here in the tissues, you had unloaded. So you're coming all the way up from the tissues here. See, PO2, 40, all through here. And then finally there. All this over here was a 40. So two things come out of this. Number one, venous blood has some oxygen in it. See, people say venous blood has no oxygen. Venous blood has some oxygen. It just doesn't have as much as arterial blood. So we really are starting right here at a 40. Now, at a 40, how much saturation do you have? See, this is a percentage. Right there, you have about that much saturation right here. Let's say at that point there. Okay? This is a 70, so it's a little bit above 70. See, that's a 70. That's 60. Now, we're going to go in here and we're going to load. When we load, so other words in the lungs, let's say you're about 100. 100 all above 104. So when you load, then this is what you have. When you load, let's say this is 100, 101, 102, 103. Check out. Now I get 100% saturation. I get 100% as much as I can based upon the iron in the +2 stage. So it's not perfect. So an oxygen sat of around 97 is good too. See, we're talking about oxygen sat. Now what happens is, the old days, the only time it was mandatory to draw blood from an artery, remember normally veins, is to do an arterial blood gas, because we're interested in arterial blood. So you'd have to keep digging into somebody and drawing arterial blood gas to see how well they're on the respirator. Now you'll have a little finger clip. Some of you know what I'm talking about. And that you'll put on there, and it shines a light, and it's a fancy little machine, and it can determine oxygen set. It's a little finger thing you squeeze on. And it's looking at a good saturation is really about a 97, 98 is good, this and that. Because you got some of that iron in the +3 oxidation state. So this direction is loading. This direction here is unloading. Now see how the line is curvilinear? What does that mean to you? That the rate of loading and the rate of unloading, change along the way. Change along the way because the line is curvilinear, which we just talked about. All right. So we load up here. So actually, right here, if we look at this being around 72, 75%, okay, so we have this thing we call the utilization coefficient. The utilization coefficient. The utilization coefficient is and see, on each hemoglobin molecule, now let's think about it. On each hemoglobin molecule, let's go here. One hemoglobin molecule has 4 hemes, and it's in the heme that the iron is. So one hemoglobin molecule can carry 4 O2s, because the O2 is hooked to the iron if it's in the +2 oxidation state. Let's look at it again. One hemoglobin molecule has 4 hemes. Each heme has an iron. Each heme can carry 1 O2. Okay, that's 4. All right. So I come back here then to this one. All right. So technically, if we were looking at this hemoglobin O2 as one hemoglobin molecule. Now I want you to think mathematically. If we were looking at this as one hemoglobin molecule, then you could either have 0 oxygens, or 1 oxygen, or 2 oxygens, or 3 oxygens, or 4, because you have 4. Now, then technically, if this was one hemoglobin molecule, all you would have would be a 25%, a 50%, and a 75, and 100, because you could only have 1, 2, 3, or 4. So then how do you have the in-between values? Because it's not one hemoglobin. It's 1 mole of hemoglobin in this curve. 1 mole, 6.02 times 10 to the 23rd molecule. See, go back to your chemistry. That means the in-between numbers are average. That means one in that mole might have 2. Another one might have 3. Or one may have 1. So in other words, it's a blend. That's how you get all these various numbers. You're looking at a mole of hemoglobin. Okay? Mole of hemoglobin. So that's another thing to know about this curve here. All right. So you're loading up. So the utilization coefficient is how many used out of how many you have. How many used out of how many you have. So we're going to stop right here and then talk about the utilization coefficient as we approach this. Okay.